Question C. By using sensible estimates for the physical quantities involved, calculate how many visible photons per second are emitted by a 100-watt hot filament light bulb. Whew. This is a pretty exciting question. So essentially what we're after here is to know the total energy emitted from the light bulb, so ET from the bulb, and we also need to know the energy per photon of visible light. Visible because we're talking about visible photons per second, visible light. All of this will take place in 1 second if we assume 100 watts is 100 joules. Okay, and the only thing is it's a visible light, and this hot is a clue. 100 watt hot. Usually you don't talk about 100 watt hot, you talk about 100 watt bright. But the filament light bulbs, as you know, hopefully know, are not very efficient. They put out a lot of heat. Okay, so we're probably going to find that about only 10 watts is actually visible light. 10 watts of the 100 watt light bulb is visible light, because energy saving light bulbs of about I think 10 to 14 watts is approximately the same as a 100 watt of filament. So that's the energy saving. This is the filament, and LED lights are fairly similar, around about 10 watts for the similar. That's for LED lighting. So I think we can assume that only 10 watts of visible light is produced. So this is going to be 10 watts or 10 joules in 1 second. Okay, because remember we're dealing with 1 second. Now, as I was saying, if we know the total amount of energy emitted by this bulb in 1 second, and we know the energy per photon of light, then we just have to divide the total 10 joules by this energy per photon. That'll give us the number of photons that are emitted in that 1 second burst. Okay. Now there's a little trick still. So one more trick. What constitutes the energy for visible light? Well, we can use E equals HF to find Planck's constant. We know. Let's just tick that. The frequency of the visible light we're going to have to estimate. Okay. So visible light is, if you're talking about the electromagnetic spectrum, it's roughly of the range 400 to 600 nanometers to 600, I didn't do that very well, but you know what I mean, nanometers. That's times 10 to the minus 9 meters. Okay, so halfway in between there's 500, which seems a good estimate for the wavelength from V equals F lambda. F equals V over lambda, so we can rearrange this to be H equals V over lambda. H we said we know, V is going to be the speed of light, so we know that, and lambda, let's just write a little c so we know that, and lambda is our estimated 500 nanometers. Okay, so it turns out if we plug all of this in, we end up with about 4 times 10 to the minus 19 joules per, let's just do that up here, about say 4 times 10 to the minus 19 joules per photon of light. Okay, so excuse me, all we have to do then is take our 10 joules, divide it by 4 times 10 to the minus 19 joules, and that's going to give us the total number of electrons emitted, and it's of the order of 10 to the 19, which makes sense because it's 10 to the minus 19 on the bottom. So you end up with about 10 to the 19 photons emitted of visible light. Okay. Now I'm just making a brief comment on this. Because your average wavelength of visible light is 500, you might say, well, there might be more at 400 or more at 600, and that could skew the amount that we finally end up with, because it skews the amount of energy per photon. If we're sticking with the average down the middle, it kind of doesn't matter, because it's going to be approximately about right. And remember, the question goes up and it says use reasonable or sensible estimates. There we go, sensible. So I think that's fair. We've done that question well.